Hi, welcome to question 7 of the work, energy and power examples. This is a bit of a nice one in order to get some insight of what work done is. And it's a little bit counterintuitive, but we'll look at it in some detail, so hopefully by the end of the video that it will make sense. The first part is very easy. Part A is just a standard work problem. It says to cut a lawn, Pedro has to push a lawnmower 80 meters. If his average horizontal push is 100 newtons, how much work does he do on the lawnmower? So this is easy because he is doing work with a force that is exactly in the same direction as the lawnmower. So if the lawnmower is here and moving in that direction, then his force is also being applied horizontally, the question says. So that's a force of 100 and it moves a distance of 80 meters. So that's easy to calculate. We just say work done is equal to the force times the displacement, which is equal to 80 times 100. On the other way around, but it doesn't matter. And 100 times 80 is just 80 with 2 zeros. So that is 8,000 joules. That's how much work Pedro does on the lawnmower. Right, and the definition of work is really the one that we're using here is that the point of application of the force, which in this case would be this part of the lawnmower, that or the handle or wherever that is, that needs to move. So if the point of application of the force moves, then we're doing work. Okay. Now, in the second part, which is a little bit more interesting, the question says, when he's finished the task, the lawnmower has whoops, so I put some space here, so sorry, let me just delete this here. I'm going to do question B here. We've already done A up here. When he's finished the task, the lawnmower has no kinetic energy, right? And this is all being in a horizontal ground. It's all happening in horizontal ground. So it says when he's finished, it has no kinetic energy. So how much work does the frictional force do on the lawnmower? So here it's a little bit of a strange concept, the idea that frictional forces do work, but if you think about it, it makes sense. If here is this is my lawnmower, and here's the handle or whatever, and the person is pushing here, pushing it forward, then the frictional forces of the grass down here on the lawnmower are going to be going in that direction, right? That's the frictional forces, and as he moves along, the frictional forces will be doing work, because that's that work that the friction forces is doing is what allows him to be moving with a constant velocity. So initially he pushes it and accelerates it a little bit, but probably then he reaches a pretty slow constant velocity, and then he keeps on pushing it. And what allows that constant velocity to be reached is that even though he keeps on pushing, there is a frictional force here that's going backwards, and so the frictional force can be seen as doing work, because the point of application of the force, which is the lawnmower, is moving in space, and the force is being applied there on the lawnmower. So yeah, he does work, but also the frictional forces do work. And if we did the normal way of calculating it, then it would be easy. We just, well, the argument that we could use would be the work done, which is the other definition of work done, is equal to the transfer of energy. And here, if we look at the work that he's doing, then we can see that the work done by Pedro, I love his name, is the same as all the transfers of energy that happen. So all the work that he does is going to go into, well, first of all, it's going to go into kinetic energy. Second of all, it's going to go into gravitational potential energy. And third of all, it could go into elastic potential energy. And finally, it would go into frictional forces. Frictional forces. But they tell us that all the work that he does, by the time he ends the task, the kinetic energy is zero, i.e. the machine is not moving anymore, so all the kinetic energy that we gave it has all gone. The gravitational potential energy is zero because it's not going up or down a hill, it's just going horizontally. The elastic potential energy is zero because we're not stretching or compressing the lawnmower. And so all the energy that he's putting in, by the end of the task, when he finishes, the friction must have done all of that work also, because that's where all the transfer of energy has done. All his work has gone into friction by the end of it. So we can say that the work done by the friction is equal to the work done by Pedro, which is equal to 8,000 joules. 8,000 joules. Okay, hopefully that makes sense. And another way of thinking about it, instead of transfer of energy, if you want to think about it in terms of force times distance, initially when Pedro starts moving the lawnmower, he's gonna have to do a bigger force than the friction, right, in order to get the lawnmower to accelerate and go up to its constant speed. So we can call this the speeding up time. Then from here to here, constant velocity. This will be the great majority of the movement. And here the forces are the same. So let me use a different color for the resistance. Let's say that the resistance is orange. Friction to motion is orange and his force is yellow. So here in the constant velocity region, the two forces will be the same. He's pushing with that much force and the frictional forces are pushing with the same force. Imagine that those two are the same size. And then here at the end, when he starts to slow down, he's not going to pull it back, he's just going to let the friction do the work. So the friction is going to be bigger, going to be probably the same size as here, although it's a function normally of velocity, but it's going to be bigger than the force that he's putting, which is going to be very small. And that way it's going to slow down. So this region here, we can call it slowing down time. Slowing down time. So if you look at the force that the frictional, the work that the frictional forces are doing, it starts small, so that this speeds up. Then it's the same as the constant, as the one that he's pushing with for constant velocity, and eventually it's bigger than this one. So all of this distance, which is 80 meters, they tell us in the question, the frictional force is actually working on the lawnmower, right? It's working on it, and here with a small force, here with a middle force, and here with a larger force than this comparatively. And his force is doing the opposite. Initially it's a little bit bigger than the other one to speed it up, then it's the same, and at the end is smaller. So hopefully you can see the symmetric argument there in terms of, well, if he starts moving it and by the end of the problem the kinetic energy of the thing, of the lawnmower, is zero, then all of the energy, since we're not going up or down or compressing or stretching the lawnmower, all of the energy must have gone into transferring the energy into energy lost to friction. So that would be heat and sound, or mainly heat and the frictional forces. Okay, so hopefully that makes sense. And then the idea of friction, of work done by friction, is one that makes sense to you now. It's very likely that you can get questions asking you this kind of thing, and even though the argument is not very difficult and the answer is the same, again 8,000 joules, it's important that you understand why, and hopefully this gives you a little bit of insight to how. This would be looking at the force times distance equals work done equation in that sense, and this looks more in terms of the work done equals the transfer of energy. Okay, either argument would be valid, but ideally you need to understand them both. Okay, so the next question I'll do in the next video, and until then, take care.